Thanks for coming. I am John Hitchingham, Director of Performance Engineering at FINRA, and I'm here today to share about FINRA's scalable analytics architecture on S3 and go into how we've recently been able to extend that architecture to include HBase. So I guess first a little bit about FINRA. FINRA is the Financial Industry Regulatory Authority. We're responsible for monitoring, for processing over 99% of all equities trades in the United States, 65% of all options trades, and we look through that looking for fraud, market manipulation, insider trading, and abuse. We process large volumes of data, over 75 billion records per day, 6 terabytes of data per day. We also oversee over 3,900 broker-dealer firms in the U.S., along with 640,000 broker-dealer individuals. And our technology team, supports the regulatory functions of FINRA through innovative technology solutions, such as we're going to cover here today. So in terms of things to expect from the session, basically we're going to go over FINRA's scalable cloud analytics architecture on S3, and also talk about how we've recently been able to take advantage of the new features, HBase on S3 with EMR, to extend it to run HBase workloads using S3 as a data lake. So maybe a good place to start is where FINRA was several years ago before we went to the cloud. I mentioned before the data volumes that we were dealing with. We were dealing with those as part of our on-premises implementation that we had before going to the cloud. We were fairly early adopters and heavy users of data warehouse appliances, fairly expensive data warehouse appliances. And we were able to use them to get the job done, but not really done well. We were having a lot of struggles that we were constantly working with. In our business, like one of the big challenges that we have is fluctuating demand, right? If there's a busy day on the stock market, the volumes could be 2 or 3 times normal. You never really know ahead of time when that's going to happen. How do you size your capacity to handle that fluctuating volume? Additionally, sometimes we have to do data corrections. We have to do reprocessing. Sometimes users want to come along and they want to do special analytics on to learn new insights about our data. And again, with the fixed capacity situation that we had, where we had storage and compute combined, it's very difficult to kind of accommodate those scenarios. Your choices are really kind of size for the absolute, theoretical worst peak that you could do in over provision, which is very expensive, or kind of size for the kind of the normal case, which is cost effective, but then that led to a lot of other challenges too, right? We found out that we're constantly spending a lot of time kind of managing the data, right? Users just wanted answers to questions. They wanted to just run their analytics, and everything we did sort of turned into a little mini IT project to be able to just get the data ready in a position where they could run their analytics. Often, if the market volumes went high, we'd have to process it to meet our SLAs. But in order to do that, we'd have to effectively kick other people off the system. So we get into a negotiation of who to kick off the system, to let the market, volumes get processed and meet our SLAs. And a lot of time talking to people, a lot of time walking around, kind of negotiating, how to live on this fixed infrastructure, right? So what we asked ourselves was, is there a better way to do this? Is there something that we could do in the cloud that we could give us scalable, flexible architecture, to kind of solve this problem? So we really kind of asked ourselves, what would be the ideal analytics environment? And I think, it's one where we would never run out of space. We wouldn't have to be constantly moving things to tape, off of our mainline storage. We'd have the capacity that we talked about, the compute capacity to spin up and spin down is needed based on the fluctuating workloads. Again, back to the capacity question, right? Not pay for oversized capacity. We want to be able to pay only for what we use. achieve isolation of workloads. Again, when everyone was using our data warehouse appliances, they were a precious resource, right? So we had to do a lot of sharing, and we're running constantly into contention between read workloads, write workloads, loading the data. If things went wrong on the batch window, people would again be conflicting. If there was a problem, someone's query was, not behaving well, you really had to kind of figure out how to tame it down, and so it wouldn't impact the other users of the shared system. So was there a way we could, in the cloud, we could achieve workload isolation too among these different workloads. And why do this, right? Because I think the thing that we wanted to do was find a way, again, to have IT not focused on spending so many resources just on moving data, managing data. We wanted to be able to really just let the business do the analytics unencumbered. So about 3.5 years ago, we started our journey to the cloud. And as part of that effort, we spent a lot of time thinking about kind of what we wanted our architecture to look like in the cloud. And this is the architecture here that we use today for probably over 90% of our processing that we do in the cloud. So maybe I can spend a little time going through it and kind of walking over it. So the key to it, as you can see, is we have S3 as our main storage layer, scalable. We can scale it out however we need it. We have a compute layer, primarily Amazon EMR, that we run to do our actual queries and analytics against the data stored on S3. And then we also have our data catalog system that keeps track of all the data on S3, and integrates in as part of an orchestration system with our analytics workloads, so we can do tracking and processing of the data. We can know where the data is, what data has been processed, who's processed it, and we can keep track of all of this out there in the cloud. So as a result of being able to move to this architecture in the cloud, as we can see here, storage, where we had the fixed limits before on our old data warehouse clusters, we're now able to scale out on S3 as our our nearline storage in the cloud, fluctuating as needed, accommodating growth, and having all that data available and accessible, so we can run analytics queries on it whenever we want. On the compute side, we have the ability now through using EMR to scale up and down based on fluctuating demand. So as you can see here, pretty severe changes, hour to hour, day to day, as we go through and we do our processing. Sometimes we run over 10,000 nodes, EC2 nodes of compute at one time on EMR. Other times we're down to just a few dozen. So this really gives us the flexibility, as I said before, as market volumes change, as we need to do special runs of analytics, we have the ability to just spin capacity up and run with it, and then just have it work. So again, we've achieved the flexibility on the flexibility and the scalability on the storage area. We've achieved flexibility and scalability on the compute area. So in terms of our approach that we take, there's a couple key things that we think about as part of our architecture. As I said before, one of the key things that we do is we register and we track everything in our data catalog, which we'll talk about in a few minutes. We keep, one of the things we do is we keep what we call sort of our archive copy of data on S3. We'll get into that in more details later, but this is sort of the golden copy of the data that we keep out there on S3. And then we make potential derivations off of if we need to for performance reasons. The other key thing, of course, being a financial regulator, is protecting the data. So we take many steps to make sure that our data is secure and safe in the cloud. Again, one of the things that we do very heavily is we try to run our processing directly against the data on S3, not load the data into our processing areas and process it, but actually just keep the data on S3 and process directly against it. And we'll talk about kind of some of the ways that we do that in a little bit. And then, as I said before, a lot of times we can run against that main copy of the data, but where we need to, we can make additional copies tuned for performant query. In many cases, still keeping the data out there on S3. So, as I said earlier, one of the real key things for our architecture is being able to track the data that we have out there on the cloud. We have over 40 million objects, we call them objects, but basically you can think of an object as essentially as a file of data, you know, a CSV delimited file of data that represents like a table logically. So we have these stored on S3 and we need to know who put it there, you know, how do I access it, you know, who's consuming it, who's producing it, you know, all these things around data management. So, you know, very early on, as part of our effort to go to the cloud, we realized that there's an ability to track all this information out there on the cloud was going to be really key, right? And again, going back several years, there really weren't a lot of solutions out there in the market. Where we found things that were just starting to emerge, a lot of them were tied to, you know, specific ecosystems like the Hadoop ecosystem, or they were even tied to a particular vendor stack of Hadoop. So we made the decision early on to come up with our own data catalog and management service. We've, you know, since named it Herd. It's available on GitHub as open source. And so really, this is the tool that lets us, you know, track business and technical metadata associated with everything that we have out there on the cloud. You know, we have the ability for producers to register the data, consumers to register their use of the data. We can provide technical metadata to use to access and query the data that sits out there on S3, along with additional business data that we may choose to store with the objects out there. So, you know, kind of going through sort of how we handle that, you know, kind of gold copy of every object or every file, table, call it what you will, that we want to put out there on S3. You know, we store it on S3. Why? Because, you know, we have the 11.9's availability, durability on S3. We have multi-AZ availability, so it's replicated across multiple data centers for redundancy and resiliency. As I said, you know, for every object that we put out there in the cloud, we track it in our data management system, Herd. You know, the storage location, the partition keys, and we'll talk about partition keys in a minute. The version, you know, logical versions of the data that we store out there, if there's changes to the data format over time, or there's data corrections to the data over time. And then again, as we'll see in a little bit later, the schema, the DDL that you would need to directly access the data, you know, and run queries against it using Hive or Spark or Presto while keeping it out in S3. We keep version history, you know, in our data catalog system, as I mentioned. This is distinct from S3 bucket versioning. So this is, again, logical versioning that we do against the data as we make changes to it. We do also, where we need, you know, take advantage of bucket versioning in S3. So that if there's some accidental change to the data or something happens, we have an older copy we can go back to and recover from if we need to. As I said, this, what we call sort of our archive copy of the data, we store it in text format, delimited text format. The goal being, as, you know, different formats and things change over the years, this is kind of like the lowest common denominator format that all tools can access, you know, over time. So we keep it in that set so that as, you know, tools and things change, we still have the ability to access and go back and retrieve and read and view the data that we have out there. You know, we compress all the data to save space. We chose to use bzip2 compression because it's splittable on MapReduce. So again, all of our what we call our archive copies of the data are you know, compressed using bzip2. You know, as I said, protecting the data is very important to us. So all the data that we have on S3 is encrypted. Depending on the sensitivity of the data, we either use SSE encryption or we use Amazon's KMS encryption using their KMS service. For actual processing that we do on EMR, I know, again, we keep most of our data on S3, but temporarily we may move it to EMR in order to do processing against it. We use LUKS encryption of the file system. We had our own homegrown one that we did originally, but now that's a product that is a feature that's supported as part of the newer versions of EMR. So we're gradually migrating over to use that. Encryption of the data in transit using HTTPS and SSL, so data into the cluster and around through the cloud. I mentioned before we use bucket versioning so that if there's some sort of issue with the corruption of the data or some sort of problem, we can go back to an older version and we have a copy there. Another thing that we do is we back up the data. Sort of this is a break glass in case of emergency kind of situation. We replicate it to a completely separate account in a completely separate region, and we control access to that very tightly so that if there's some sort of catastrophic problem in where our main account is with the main set of data, we do have a copy that we can go back and pull back from from another region if we need to access it. So I said earlier, I've talked a little bit about sort of this idea of storing technical metadata, DDL, so that you can actually query the data. So one of the things that we do, and it might be a little hard to see up here, but what we do is we generally, in all of our processing that we run on EMR, using Hive, using Spark, using Presto, we define external tables. So we have the data set sitting out there on S3. We define them as external tables, and then we can bring up an EMR cluster, and we can run queries, we can process against the data, leaving it out there on S3. There's a lot of benefits for us to do this, because we can then basically, our clusters, we don't have to spend all the time it takes to load the data into the cluster before we can do processing. If we want to do basically queries against years and years worth of data, it's not practical to load all that data in the cluster, just to do like some queries against it. We can just start processing against all the data that's out there on S3. The other advantages of this too, we do checkpointing as part of our batch workloads as we go along, so that lets us run a lot of things on spot. So if we lose the cluster, we don't have to reload all the data back in order to start processing again. We have the data out there S3, we just bring up a new cluster and start processing again where we left off. As I said before, we talked about our data catalog system, HERD, where we keep all of our metadata, the main copy of our metadata. In a couple of cases, we've done some optimizations on that. One thing that we've done is we've created, a persistent shared Hive metastore, keeping the latest, the metadata for the latest version of the data. And we do that so that when we bring up clusters, Hive, Spark, Presto, instead of having to have custom handlers that would talk to the REST service API that our HERD data catalog represents, they can just speak natively. They all speak, Hive metadata, syntax to be able to understand and interrogate it and understand what's there. We can just bring them up, and instead of having to define all these things up front before we can actually start execution on a cluster, all the metadata that's there that we need to query against is up, it's available, and it's ready to go. And there's very, low cost to that to actually, hold it all. We keep it in a small RDS database. And so at that point, we can bring clusters up and start processing against the data on S3, instantly. And we have separate schemas in there that we do to support, different versions of Hive, as sometimes the metadata changes, and then Presto originally, because that was a little bit different too. So I said before that we have all these files out there in ASCII format, bzipped out there. In a lot of cases, where performance really isn't a big deal, we can just go and process against those directly, mount them up as an external table, spin up a cluster, define it as define an external table in the metastore, spin up a cluster, and go process against it. In some cases, though, we, for better performance, we'll essentially make a more performant copy of the data. So we'll go through and we'll, basically change the partition keys potentially, or the sort order to better fit the query patterns that we want to run against it. Again, in most of the use cases, we're still keeping the data out there on S3. We always try to do that wherever possible. We may also look to, change kind of the storage format into one that's, more efficient for a lot of the queries that we do. So in our case, we've settled on using the ORC format to do that. you could use Parquet too. Back at the time, several years ago, we made the decision at the time to go with Orc. And so, that's what we use today. But basically, that gives us a lot more efficient, query response time for a lot of the queries that we do. Does that show up? Yeah. So just kind of as an example on that, right? Here's some test queries that we've run. So this is going against over 2 billion rows of data, not partitioned, and you can see the difference between if you run these queries against a text file format in bzip and the response times that you see there, and having it in the ORC format. So again, if you're not doing complete full scans, pulling all, doing a complete copy of all the data, there's a lot of efficiency you can gain by switching to a format like ORC or Parquet, for your performant queries. Again, we choose to make that copy for performant query, so it's almost kind of like part of a, kind of a data mart, that we create off the main data. We leave the main data still in ASCII. That's our golden copy format that we can always go back to if we need to. So, kind of again, sort of the benefits of this architecture, right? If we, use S3 as our storage layer, we have, security and cost efficiency by storing it on S3. It's a very cost-effective way to store your data, and it scales. And we, just don't have to think about it. It's just there. We don't have to manage the data. We don't have to worry, the space, or we don't run into those problems that we ran into on the on-premises environment that we were on before. As we said before, keeping the data on S3 lets us, bring our compute layer to whatever size we need to run against S3. So, and that's a question of not just, an individual cluster, size to whatever we need. We can run multiple clusters, multiple analytic workloads reading off the same data set at each time. So in some cases, we can have, dozens of EMR clusters going off the same set of data on S3 doing their processing in parallel. So it gives us parallelization at the compute layer too. As we said, avoid copying of large data sets. If I want to go through a huge set of data but only extract a few things, we can go ahead and we can do that by keeping the data on S3. And as I said before, also it lets us use a heavy use of Spot as part of our processing. So kind of going back to the beginning on this, what does this do? By really moving to this architecture in the cloud, we really aren't focused anymore on the management of the data, the moving the data in and out, the tracking, the manually tracking where it goes, the fighting for the limited batch windows that we had as part of our on-premises solution before with the data warehouse appliances. So really, feedback from some of our business users on the system is that, it lets them really kind of focus on just getting their job done working with the analytics. So, if they want to run queries against the last 7 years worth of data, they can. The data is on S3. We have query clusters that are up and running. The data is all referenced in our shared meta store that we talked about. So they just come on in, boom, and you're off and running against up to 7 years worth of data instantly. We're no longer contending, sort of processing the conflicts between the workloads. We can spin up multiple individual clusters if we run out of capacity and we need extra capacity. If the business comes to us and they want to do some sort of new special analysis, they can just spin up a cluster and start running it. They don't need to, again, fight for limited batch windows. And we can access, again, all this data as it grows out there on S3. So, the architecture that I just described has worked really well for us, but it's really been tied so far to the tools of, Hive, Presto, Spark. And what we asked ourselves was there a way that we could extend the benefits of that architecture to cover our HBase applications? So we have a couple HBase applications that we run in the cloud, and we wanted to say, historically we hadn't been able to leverage that same architecture with those, and was there a way that we could extend this to do that? And so I want to talk a little bit about one of our applications that uses HBase. It's called our Fast Order Lifecycle application, or we call it FOLA. And basically what it does is, it tracks market events in the market. So if you have an order and a series of trades that result from that, they really become part of one chain of events that we call an order life cycle. And so what our analysts need to do on a daily basis is, given like a particular event, they need to understand what chain is that event part of, and be able to pull back the full set of events that are really part of that chain, and then display the results so that they can see them, and do their analysis on it. It's a bit challenging because, again, there's trillions of events out there, and we're adding billions a day to the database. So we came up with an approach to query the data to get the results back. And what we do is it's a series of basically 3 different lookups. So given the event that we want to look for example, in this case, event number 3, we go find out, we do a lookup to find what group or set is it a member of, right? So it's a member of set B. So we go back and we do another retrieval to find out what's the set members of B. Once we have those, we can go about in parallel and go do basically lookups to retrieve back all the members of the set then and get the content or the data that's associated with each of those IDs, and then display it back to the user. But again, we're trying to do this in a random pattern across trillions of records, comprising hundreds and hundreds and hundreds of terabytes of compressed data. And we need to do it with high read concurrency and get the results back in a few seconds. We looked at, at the time we were using Hive, the ability to kind of do these retrievals randomly across this data set and get response time in a few seconds, not possible. So that took us, to an HBase solution, which we built, which we'll talk about in a minute, that we built as we went up to the cloud. So this is our original solution that we built in the cloud. And it was really kind of it was really more of a lift and shift kind of approach for what you might build in a data center. We had over 60 HS1 8X large machines where we were, again, combining storage and compute onto the same machine. So, we built that up pretty early as a part of our migration to the cloud. And, it was a solution that from a business perspective worked well. Users were able to get results back using the HBase architecture much, much faster than they were with the prior system that existed, in our data centers on premises. So that was good. But again, by binding the storage and the compute together, kind of going against the grain for our overall architecture that we talked about earlier, it presented a series of challenges, both in terms of operations and in terms of cost. So, from the operational front, we always had backups that were exceeding the maintenance window. So we have a cluster of EC2s, the data's on the EC2s, we triple replicated with replication on Hadoop, but if you lose enough nodes, your cluster's down and you have to recover. Well, so we make backup copies to S3. The trouble is when you start talking about 700 terabytes of data that you have to back up off the cluster to S3, that takes a long time. So we started to get, our data footprint started to get so big that we really didn't even have a backup window anymore where we could make the backups. Same thing going the other way. If we were to lose the cluster, the amount of time that it would take to restore and rebuild the cluster and restore was basically exceeding our recovery time objective, that we had to be back up and running in the event of a failure. So again, we had a copy of the data on S3, but to get it back up into the cluster and get back up and running was taking longer than we had to do it. Another thing is, we talked earlier in the presentation about the importance of security to us. One of the things that we do is we make sure that we're constantly upgrading and effectively patching our systems by upgrading the AMI to include the latest version of an AMI that's out there, the Amazon Machine Image. And when we have a cluster that we treat kind of like just much like you do on premises, changing those AMIs got to be very difficult. You would have to either build a completely separate parallel cluster on the new AMI, back up all the data to S3, restore the data from S3, which I talked about before was a really cumbersome process. Or in some cases, you'd have to pull out an individual machine, upgrade it, put it back into the cluster, rebalance all the data, which again took a long time. So upgrading was very painful. And internally, our security team, working with the team that builds our AMIs for use, is basically upgrading them once a month. So it really wasn't just practical to kind of keep up with that kind of velocity. And another thing, just in terms of the nature of the application, I kind of talked about sort of the query scenario before that we run on the cluster. The way the data gets loaded is it gets loaded via a batch process to get loaded into HBase. That batch process runs on the same cluster, but sometimes, again, due to fluctuating market volumes or potentially having to pause processing while we, in response to some data corrections upstream, we can get behind. And again, when we get behind, we run into situations where the batch processing window starts to crowd into our query window, and that causes conflicts. So again, trouble living within the limits of the storage and compute on the cluster. And another one, quite frankly, was cost. So we had data growing, at roughly 20 terabytes a month on the application, and the nature of the application was such that we were really storage bound on the cluster. There was not a lot of heavy compute load that was there, but the only way you can store that much data is to buy these HS1 nodes, or today you would buy D2 8X larges, and these are very, as people probably know, these are very expensive machines. So we're spending a lot of money just to store the data, and with a lot of extra compute that really we couldn't use or didn't have a need for. So again, we asked ourselves, is there a way to kind of address these challenges and move more to an architecture which we use for the vast majority of our other processing? And so again, what would it be? We asked ourselves, what would it be like if we could store the data out on S3? Well, what would be the benefits? We could have a single copy of the data. We wouldn't have to have it triple replicated. Lower storage cost. Again, the things we talked about before, we could have new compute available to run against it in minutes versus the several days that it would take to restore before. We could start to separate out the read query cluster from the batch processing cluster, much as we do with the rest of our architecture. For disaster recovery, I talked about the scenario where we could lose a cluster. Well, if there was a problem within a particular availability zone, same thing. We can basically, we could want to be able to fail over and be up and running in another availability zone, in a very short period of time, not the 2 days it would take to restore otherwise. So, working with Amazon and the EMR team, we ended up with our new HBase on S3 architecture, which we'll talk about a little bit here. So we worked with the early version of HBase on S3, which is now generally available on EMR, and we implemented it and went live over the summer. So real changes here. Again, the data now is stored on S3. All the H files as part of the HBase operational store, they're stored on an S3 bucket. We have a cluster. You can see on if people are looking there, the node sizes are much smaller. Instead of those HS1 8X large, very big, expensive, lots of compute nodes, we run M3 2X larges now against that, so we can size the compute independently of the storage now as part of the cluster. And then, as I said before, we can now separate out, and we have a separate cluster that actually does the generation of the batch processing that generates the H files for load into the database. So we can run that now also on Spot for additional savings, because if there's a problem, we just stop, as we talked about, we just stop the cluster, restart the process, and then complete the processing and load the data. A little bit about the application itself. Why we thought that this, HBase on S3, even back when we started this, could be a good fit for what we do. It's a read-only application. We don't use puts as part of that. I know as part of the actual GA available version of HBase on S3 now, there's been a lot of effort that the team's focused on to support that use case. But for us, that really wasn't part of the equation, because we really don't do puts as part of the application at all. We have the random read pattern to retrieve records across all the data. And as I said before, the loads of the data, because we're not doing puts, how does the data get into the system? We use the HBase bulk load API to load the data. So we're able to process it, bulk load it into the system, no puts against the system, no writes through the mem store and everything into the database. And so I think the other thing is too, we did see a little additional latency by running queries against the data on S3. versus running them against local disk. But as we'll see in the next slide, we're still getting results coming back in a few seconds for the application. So if you can see it up there at the top here, the response time for the queries, the majority of the queries that people run have result sets about 10 records or less that come back. So that's about 62% of the overall query base. And they're coming back in a few seconds. So again, within the range of what you'd be looking for an interactive query type application. And again, just to kind of level set on that, as I talked before, the on-premises implementation of the system before we went to the cloud, results were coming back in tens of minutes to hours, right? So again, we're getting performance that's within what you'd expect off of a Presto or a Hive is running your queries from what we saw from some of the earlier slides. But again, we're able to do that against random access across trillions of records and hundreds of terabytes of data. So, sort of a little bit of hit on the performance side, within the acceptable use for interactive application, what are the benefits, what do we get? So we talked about some of that already, kind of as the other side of the case. So now we can restart the cluster, in 30 minutes if we need to. Again, before starting a cluster from scratch, would have been a multi-day exercise. If we want to do, automatic node replacement, if we lose a node, EMR will just replace the node for us and put a node back in so we can continue processing. Easier AMI updates. If we want to update the AMI versions on the cluster, we can just go ahead and, kill the cluster, restart it back up as the new AMI and be running. Again, restarting in different AZs, we can do that. And then we can, separate the traffic as we talked about before. The last one up here is worth noting too is, again, we can easily scale the cluster up. So if we need to add 100 nodes for whatever reason, because there's a spike in user traffic, that's something that we can very easily do. That doesn't really come into play much in our current application, but for some of the other use cases that we're looking to extend this to, that can become very important. So that's another capability that's going to be important to us. Sort of on the other side of the equation, on the cost side, right? I mean, by keeping the data on S3, brings up a lot of advantages we weren't able to take advantage of before in the HBase architecture. We can run the less expensive nodes. We can scale the cluster down at night for additional savings. So we can run more nodes during the day when the users do their processing. We can scale down to a smaller number of nodes at night when the query traffic is minimal or very low. We can run the batch process separately from the main cluster. Another big thing that we do is in our lower environments, dev and test, right? Before we had to have kind of an always-on cluster there to have, because again, the setup and the teardown of the cluster was such an exercise. Here it's very easy to bring the cluster up, run it on Spot. We run the Spot in the lower environments, do any sort of testing we need, and then just shut the cluster down when we're not under active development. And that's actually been a big savings for this particular application because it's not really under a lot of active development. It's kind of in a maintenance mode right now. So before, where we had to have lower environments, provisioned and ready to go, now we can basically just, have nothing there effectively. If we want to run, we can make a copy of the data, spin up a cluster and be up and, working that way when we're actually doing active development on it. A little bit about, kind of talking about some of the settings that we made. This talks a little bit about our cache settings on the cluster. One of the things we did is to get some better performance off of S3, we set the cache, the indexes in the Bloom filters on the H files. The data set size is such we can't cache all the data. So we decided to basically kind of cache those. So as we go back and do additional retrievals, we'd have those things loaded up into memory to speed up, the processing for the next data sets that were coming back. We chose to basically configure that by doing that such that it would be cached to disk. So we run SSD disk, and we cache the data to disk on cluster to really maximize the amount that we can cache on the cluster. We did have to make a few changes, kind of how we do things, because we're using S3 as a storage layer instead of HDFS. Primarily, these were really around the areas sort of some of the timeout processes. There's a few things in HBase where it thinks you're using an inode-based file system or logical or physical, such that if you want to do a rename operation or a move operation, is expecting that to happen very quickly. There's not many cases where that happens, but where it has, we had to kind of bump up some of the timeouts and take more care as part of those operational tasks when we do them. So potentially schedule them during a batch window or something like that in order to do them. Just a couple other things too that we kind of saw. One was just, this is not really related so much to the HBase on S3, but just based on the large number of HBase regions that we have, if a particular node were to go out, EMR automatically moves the regions over to other nodes, region servers on other nodes, such that the processing can continue uninterrupted to the users. We did find when we automatically add a new server back in as part of EMR that there was a lot of load that was generated as part of the rebalancing, just because in our case we have so many regions across our region servers. So we just made a decision basically to say, if we lose nodes, it'll let EMR automatically reallocate those to continue processing, and then when we add a node back in, we can do a manual rebalance by running a script. It's very quick to do. We just do that, kind of off hours as part of a maintenance window. And then again, a couple other things, kind of differences between running it on, file system, HDFS versus S3. Some of the operation, the metadata operations, like, drop table and things are slow. But again, in a production environment, that doesn't really, cause us any problems because we're not doing that kind of stuff. It does come up sometimes when we're under development and dev and test, so we have to do some kind of workarounds as part of that. Another, kind of big thing that we ran across, again, using S3 as a storage layer, was there are a few, kind of operations that are, very, very write processing intensive, write intensive against S3. And what we found, during major compactions and export snapshots, things where we're, doing a heavy amount of write processing against, S3, we were running into bottlenecks on S3. And I think, sort of the standard practice is, design your key structure, your file structure, basically, so that when you're writing to S3, you don't collide on the same lexicographical space as you're doing your writes. That really wasn't possible in this case. We don't really have control over what that key looks like. We just have to accept what's there in HBase. So, we worked with our account team to engage the S3 team to do some pre-partitioning on the bucket at the right point in the key space, such that, when we did writes, we get much better performance, of those going through. So, in terms of further areas of investigation, that we're going to be looking at as part of HBase on S3, is there a way to take better advantage of the caching capabilities that are out there? We kind of did some basic first level caching to get out the door, but we think that there's other things that we can look at in terms of, potentially doing more sophisticated pre-warming of the cache. Today we just basically cache, upon access, but we've looked at ways, is there a way to pre-warm against a lot of the data out there to get even faster response time for first access? Looking at just, can we use it and leverage it for more write-intensive workloads, as part of the new GA version that's out there for HBase on S3 from EMR. One of the things we want to try to do, and I think this will probably require an HBase change, but we're looking at it, is the ability to run multiple clusters against a single operational data store on S3. In HBase right now, the ability to run multiple clusters is limited because they essentially collide on the same metadata portion of the database. So is there a way to basically have them coexist and run together? And then one of the things we want to look at too is, can we put a SQL interface on top of all this? Today we basically just use HBase API calls, custom code to access it. But in this kind of architecture, could you also put Apache Phoenix in front of it and run SQL queries against this? So that's something that we want to look at and want to try. Some other FINRA sessions here that are here that folks can either have checked out or still to come. So again, thanks for coming. And appreciate sharing kind of our architecture on S3, scalable architecture in HBase. And I think for questions, I guess there's a microphone here. So if anyone has any questions, you want to come up to the microphone, you can ask them. Or if you have any questions afterwards, feel free to stop by and ask.